Hi, my name is Anna Wadhwa, and with the support of Dr. James Maclaurin from the New Jersey Institute of Technology, we investigated the effects of colored noise on neuronal activity using the Fitzhugh-Nagumo model. So as an overview of what we'll cover today, we'll give a little bit of background on the FHN model, how it's used to understand neuronal signaling in different noise structures, and then we'll go into some detail about how these affected the excitatory and refractory variables independently, and why this was interesting in blue noise especially. So in order to understand the Fitzhugh-Nagumo model, we want to be looking at neuronal action potentials, those electrical signals that are transmitted between neurons. And it's a system of two differential equations. We have dv/dt and dw/dt. V is our excitatory variable on a fast time curve and roughly relates to the voltage potential of the membrane. W is the refractory variable on a slow time curve, and it roughly corresponds to the proportion of open ion channels in the membrane. And it's kept small with our constant phi, which is less than 1 to ensure that dw/dt stays low. A and B are just constants, and then I is our external current. However, the actual brain is not as simple as this. There's oftentimes lots of noise and distracting stimuli that are competing for neuronal attention. And by increasing or decreasing voltage, this noise can promote or inhibit neuronal signaling, respectively. And there's different types of noise. We have white noise, which has an even intensity at all frequencies, and we have colored noise, which is more skewed. So what we did was we created a whole bunch of MATLAB models, keeping our values for A equals 0.7, B equals 0.8, and phi for 0.8 constant. We varied current from 0.5 to 1.5 volts for the neuronal action potentials. And then we created noise structures. White noise was just a normal distribution, and colored noise, specifically pink, blue, and violet, were taken as Fourier transforms of the white noise with the power spectral density relationships listed here. So with white noise as 1, pink was considered 1 over f, blue was f, and then violet was f squared. And we were independently examining the excitatory and refractory variables. So first, to establish a baseline for the effects of noise, here we have a model without any noise added. We see there's nice even equilibriums, no fluctuations, anything like that. Here, with white noise added, we see how it causes fluctuations in signaling at low currents, moderate currents, and high currents. And these were corresponding to perturbations in our phase plane analysis. Now looking at our colored noise, we have our white noise here as a baseline, and our excitatory and refractory variables independently. In pink noise, we can see how it caused these minimal fluctuations in both variables. Blue noise was interesting in that it caused these large fluctuations in the excitatory variable without a large corresponding change in the refractory variable as well. There were some, fluctuations, but they're not huge. Violet noise caused these huge fluctuations in both the excitatory and the refractory variable. And so what we can learn from this is that noise is causing disequilibrium in neuronal voltage, and therefore it can promote or inhibit firing randomly. Pink noise caused fewer fluctuations, violet noise caused large fluctuations, and so we think that this may mean violet noise makes neuronal behavior more erratic, but since the fluctuations kind of cancel out per se, they don't specifically promote or inhibit neuronal activity in either way. Blue noise was interesting, as mentioned, because of its increase in the excitatory variable without that kind of corresponding increase in the refractory variable. And so it may kind of represent this sweet spot, quote unquote, for the promotion of neuronal firing through stochastic resonance. And this is not an unprecedented idea. This kind of stochastic resonance or Gaussian noise improving weak signal transmission has been observed in individual neurons. And it's also in line with what we've seen empirically of shifts in the noise power spectrum in the brain. Over long periods, such as aging, we see that the power spectrum shifts to lower frequencies. So for example, from blue to pink. And so if blue noise is indeed more neuronally active, then this could mean it corresponds to declines in cognitive function that we see during development or aging. Our references and acknowledgements, thank you to Dr. Kyle Dabachevsky and the NJIT Dean's Fund for Student Development for supporting this work. And also thank you to you as well for listening. Please do feel free to reach out with any questions you may have. These slides and more information is available at tinyurl.com/NEBEC-Wadhwa. Thank you.